We'll now focus our attention on ocean trenches. These features are located primarily in the Pacific Ocean, specifically concentrated in the western Pacific Ocean, and represent the deepest points on Earth. What are trenches? How did they form? And why are they mostly in the western Pacific? Plate tectonics theories, both uniformitarian and catastrophic variants, explain trench formations in the same way. The only real disagreement is over how long the process has been taking place. Uniformitarian plate tectonic theory says seafloor spreading and plate subduction represent hundreds of millions of years of time. Catastrophic plate tectonics theory says that essentially the same process occurred quickly during the flood and then slowed over time to its present rate. We see this dogmatic explanation for trenches repeated so many times by both evolution and creation proponents that many just accept plate tectonics as a fact, and the only thing argued over is how long it took. Few have considered the forces and mechanisms required for plate subduction at any speed to actually occur. Because of this, it is important to take a critical look at this popular theory. Then we will see a completely unique and much more plausible explanation from hydroplate theory. The first problem for plate subduction is getting started. Crustal plates are said to be 30 to 60 miles thick and float on the surface because they are not as dense as the mantle. This should raise eyebrows when contemplating how the edge of one plate begins to dive under another plate. Again, we'll begin by studying balance of forces. The weight of the plates is equally resisted and supported by the mantle. Pressures along this horizontal plane are relatively even. But getting a thick slab of rock to depress into the mantle means that the resisting forces in the mantle would exponentially resist any downward movement, especially when the diving plate is less dense than the material it is said to have subducted into. A similar scenario can be experienced in a swimming pool with a foam mattress. Grab an edge of the foam and pull it down below the surface. The difficulty increases as you pull down. In the pool, we provide the unnatural force needed to pull the foam under. But what force could counteract the huge resistive forces in the mantle while a 30 to 60 mile thick plate drops under another? With plate tectonics, equally artificial forces are imagined. Plates are said to have become cooler and denser so as to initiate a dive. Also, the mantle is pictured as a viscoelastic material in spite of much seismic evidence that it is solid, which makes the problem even more difficult to explain. Catastrophic plate tectonic theorists speculate that as the flood began, the edges of the plates suddenly dropped in temperature by more than 700 degrees Fahrenheit, while at the same time the mantle softened so the cold, dense plates could sink. This is all very convenient and perhaps makes their computer simulations give the answer they were looking for. But as a mechanical engineer, this heat transfer scenario baffles me. I don't see what could cause such a large mass to get that cold, nor how it could stay that cold while diving through much hotter material. When questioned as to how this could happen, the lead promoters of catastrophic plate tectonics have yet to provide any verifiable justification. Another problem is that the strength of crustal rock can support a vertical surface that is only 5 miles high, yet these plates are estimated at 30 to 60 miles thick. So the material of the overlying plate would deform and push into and against the diving plate. The shear strength of this material would have to be overcome by the diving plate as well. The sediments that are found in trenches are layered, and the layers are not disturbed. But if movement has been occurring due to a diving plate, these layers should show signs of disturbance and folding over on themselves in the direction of movement, but this is not observed. Even if a plate did manage to dive under an overlying plate, the weight of the overlying plate would scrape away anything that was not an integral part of the plate itself. Subduction proponents often imagine ocean sediments and water being dragged down along with the plate, but the pressures between the rock at these great depths would not allow this loose sediment and water to dive against a rising pressure gradient. Of course, plate tectonic theory needs water to be dragged down by the plates because this is the theory's mechanism to explain magma chambers and why volcanoes release so much water when they erupt. However, hydroplate theory provides a plausible explanation for both deep water and magma chambers which does not require a diving plate, nor miraculous conditions to produce them. Of course, plate tectonic theories also need sediments to disappear back into the mantle because if they were scraped off and piled up for hundreds of millions of years, no trench would exist. Diving sediments on a diving plate is failed logic from a failed idea. Another problem that is never addressed is that we are always shown a perfect straight-line subduction scenario. Only 2D section views are shown or discussed in any detail. but trenches where subduction is supposed to be occurring are curiously arc-shaped. When movement along the realistic arc shape is considered in 3 dimensions, subduction looks very unlikely. If scrutinized properly, this should raise some fundamental questions about the subduction theory versus basic observation and known material mechanics. Whether the material is rock or a piece of cloth, the geometry requires the same conditions if a plate is diving at an angle. If the plate is diving along such an arc, the material must be converging as it moves. Yet the material evidence of this convergence is completely missing along with any mechanical explanation for why the convergence is occurring. The 2 sets of black lines represent vectors of movement of the subducting plate. The arc requires that these vectors be angled with respect to each other, so there must be both a forward and a lateral component to the movement. This lateral component should be compressing, folding, crushing, and thickening the plate as it converges. A similar problem exists if the arc is oriented in the opposite direction. All trenches have an arc shape. True subduction could only occur if a plate is diving along a straight line, but of course, many other forces and features of trenches show that subduction has not occurred. Dr. Brown lists 17 specific reasons for this. Plate tectonics is a myth. The topography of plates diving in front of arced trenches should have a radial pattern of folds or mountainous chains in the compressed plate radiating out from the trenches. Yet these are absent from the seafloor. Trenches many times are linked in a repeating arc cusp pattern. 2 adjacent arcs mean that the plate is diving toward 2 separate points. The lateral components of these separate movements should be tearing the plate apart, or at least show signs of dramatic thinning as the material dives in 2 separate directions. Consider the arc cusp trenches east of Japan. If the oceanic plate is diving down, then it has to be diving in several directions at once. Likewise, there should be rifts or valleys indicating the plate is tearing apart as it separates. Yet again, the topography on the seafloor shows no evidence of this movement of the plate in different directions. Finally, let's assume a plate has successfully plunged into the mantle to a typical depth cited by proponents of plate tectonics. We'll just look at a first-order analysis of forces involved with even a perfect world plate diving along a straight line in a 2D scenario. Green arrows represent forces that will allow the plate to dive further into the mantle. Red arrows represent forces that prevent movement into the mantle. Red and green arrows are in a tug of war, and the question is, which one would we expect to win? First, sum the green dive forces that would allow further penetration into the mantle. Let's just set the width along the plate to 1 centimeter. We'll again give plate tectonics the benefit of the doubt by assuming no tension crack forms as the material bends down. This will allow the highest possible loading of the plate to support a dive. Assume the plate is evenly pushed into the mantle at the material's maximum compressive strength. It is physically impossible to compress higher than the max compressive stress, as it would crush the plate rather than transfer load to the diving portion of the plate. Then we'll add the component of the plate's weight that would pull it deeper into the mantle. Plug the numbers into the equation and we get 515 billion newtons per centimeter, which works out to 116 billion pounds of force. Now sum the red restrictive forces, which consist of friction above and below the plate, plus whatever head-on restrictive forces are acting in front of the plate. First, be generous and ignore the resistive forces in front of the plate, since we don't know the shape anyway. Now we'll just sum the frictional forces above and below the plate, and again plug the numbers into the equation and we get 16.5 trillion, not billion, but trillion newtons per centimeter, or 3.7 trillion pounds per centimeter. Now let's compare the results. Obviously, the red forces easily win the tug of war. Friction forces alone are over 30 times greater than the subductive forces. A plate cannot subduct. Questioning if the mantle could be viscoelastic is highly imaginative, but is also highly unlikely based on all the seismic evidence that it really is solid. Any explanations of lubrication suffers from then having to explain the origin of the lubricant. Something is wrong with plate subduction theory, and as more information is collected, the evidence against plate tectonics and mantle convection continues to mount. So much so that I was surprised to see this admission in Wikipedia's plate tectonics page. Clearly, trenches are deformations of Earth's surface. Therefore, understanding trenches should first begin with understanding the failure mechanisms of a material and recognizing how any of them deform. Pausing to do this is essential to reaching correct conclusions when performing a material failure analysis. For engineers anyway, skipping these steps and injecting a preconceived idea usually results in frustration and many hours wasted trying to validate an alleged failure mode. So first we should consider what forces could cause a spherical shape to deform in such a manner that its surface deforms into an arc and cusp shaped pattern as we see in trenches. Ping pong balls help us see that either an external force like my thumb or an internal force which causes the surface to collapse inward will readily produce the characteristic deformation we are interested in investigating. An external force is very unlikely, so the force that caused the western Pacific surface of the Earth to collapse or subside must have come from inside the Earth. One important clue is to realize that the western Pacific antipode is the middle of the Atlantic Ocean. So if you were to dig a straight hole from the middle of the western Pacific, about which the trenches are concentrated, through the center of the Earth, you'd exit in the middle of the Atlantic Ocean. I'll also point out that obviously, looking at the map, we see the arc-cusp deformation lines are not closed pattern as with ping pong balls. However, notice that the mid-oceanic ridge runs diagonally across the southern end of the Pacific Basin. Remember that the mid-oceanic ridge is a series of deep tension cracks that were already fractured by the time the forces on the Pacific plate to the north were acting. So this portion of the plate and mantle had already failed, so the characteristic arc and cusp chain did not deform in this location. Here's a better view using a globe. A straight line through the center of the Earth at the red push pin exits the Earth in about the middle of the Atlantic Ocean. Let's go back to the graphic we first used in describing how the Atlantic seafloor rose up, causing a chain reaction which led to much movement and the melting of the inner Earth. We'll quickly review. As the Atlantic floor buckled and rose up, it could only move by shearing, which produced friction and heat. As shearing continued at greater depths, the heat generated melted the shearing surfaces. Once melting occurred, this caused a runaway cycle of contraction and shifting and more melting. The direction of shift was always toward the rising Atlantic floor as more material shifted toward the contracting magma. We will now examine the effect these forces had on the opposite side of the Earth, which we've just seen happens to be the western Pacific seafloor. What was felt as pushing up for the Atlantic was felt as pulling down for the Pacific. Eventually, the Pacific hydroplate subsided and collapsed in on itself as it and the mantle both sheared and were fractured, creating many deep faults in this area of the mantle. As the central portion of the Pacific plate and mantle subsided, it sheared diagonally away from the surrounding material. The Benioff zones that plate tectonic theorists believe to be diving plates are actually the result of another well-known failure mode studied in material mechanics. When a finite element is placed under stress, its principal stresses, represented by the yellow arrows, cause the material to experience shearing forces, represented by the blue arrows. If the material fails in shear, the angle of the shear plane, represented by the black line in the square element, forms roughly 45 degrees from the element's principal stresses. For the mantle, the principal stress directions were toward the rising Atlantic and toward the center of the collapsing Pacific plate. Therefore, it sheared diagonally downward, forming a shear plane, which so many mistakenly believe is a diving plate. If interested in more detail of why materials shear in this way, study an engineering material mechanics textbook, focusing on the chapter describing Moore's circle. Or if you just want to see it happen, take a piece of chalk and twist it without bending, pulling, or compressing it, and you'll see that it shears spirally along a roughly 45-degree plane. For a time, the Earth's shape became very irregular. The movement of such large volumes of Earth's surface would have greatly affected the atmosphere as it rushed in to fill the sudden void, causing a sustained wind due to the sudden low pressure in the Pacific. This is likely why Genesis 8:1 records a great wind passed over the Earth. Because the Earth is not a tiny ping-pong ball, its gravity eventually pulled it back into a scarred yet spherical shape. The deep arc and cusp-shaped surface scars are seen today as ocean trenches. We will now focus on the heavily fractured central portion of the Pacific mantle and plate because this region is key to understanding why continents are slowly moving today. Plate tectonic theory presents Earth's surface as covered with many floating plates, shown here with red arrows indicating each plate's movement based on its main tenets, that the seafloor is spreading at the mid-ocean ridges where the new crust is being made, while older crust is diving under adjacent plates at ocean trenches. As you can see, many times edges of some plates are shown to be moving perpendicular to each other. If this is correct, seismic data collected of continental shift should validate this chart. Interestingly, the data does not support this at all. Rather, most earthquakes around the Earth indicate surface shift toward the western Pacific region we've been discussing. As stated, the Pacific hydroplate and mantle below were severely fractured as they collapsed and subsided. This exposed many deep fissures to the surface, and magma above the crossover depth spilled out en masse over the face of the Pacific plate, which essentially buried it under the expanding rising magma. The western Pacific has over 40,000 underwater seamounts that are at least 1 kilometer high, or 0.6 miles high. That's the highest concentration of volcanic seamounts on Earth. This dense population of volcanic mountains is compelling evidence of a great deal of deep fractures in the mantle below. In many places, the magma continues to be produced along the deep faults and continues to rise and spill out, forming huge underwater volcanic mountains. Some have risen above sea level, forming many Pacific island chains like Hawaii. We will now discover the mechanism behind why almost all earthquakes shift the mantle's mass toward the fractured western Pacific region. Watch the thin white lines, which represent how the mantle moves as magma is produced in a fault and then is distributed. For any deep sheared fault, magma produced along the fault that is above the crossover depth will rise and expand the upper portion of the mantle as it climbs. These properties of magma explain why the number of earthquakes at specific depths varies the way that it does. Most earthquakes are shallow and occur well above the crossover depth. This is because magma is expanding as it rises. Near the crossover depth of approximately 220 miles, there are significantly fewer earthquakes because magma produced at this level is the same density as the surrounding solids, and therefore does not tend to move up or down and cause earthquakes. Below the crossover depth, we see a second peak in the number of earthquakes. Again, this is because magma is on the move, only headed down to Earth's outer core. However, because the crossover depth for magma is only about 220 miles below the surface, for any fault filled with magma, there is over 7 times more magma below the crossover depth than above. As magma is compressed and falls toward the Earth's outer core, its volume reduces, and the overall effect is that the mantle as a whole shifts toward the fault. It is a case of volume out must equal volume in. If deep faults were spread evenly around the Earth, we'd expect somewhat random mantle shift directions. However, most deep faults are concentrated in the western Pacific region as indicated by the tremendous amount of volcanic activity. Only hydroplate theory explains why this is, and why the mantle today slowly shifts toward this region. As magma is produced over time along these many faults, it either rises up to the Pacific floor or falls down to the outer core. Again, the driving mechanism is gravity. As volume leaves the mantle in this area, the mantle must shift toward this region to fill the void. This map of actual seismic data shows this general shift toward this region of the western Pacific. Only hydroplate theory explains why this shift occurs and why it points to the western Pacific. Of course, as earthquakes occur, scientists can now measure slight changes in Earth's rate of spin, which generally spins faster with each large quake. This is because most magma produced is basically mass that is being compressed and moved toward Earth's spin axis as it travels to Earth's liquid core. Why this happens is explained by the law of conservation of angular momentum. Consider the technique of a figure skater in a spin. Arms and free leg enter the spin outstretched. The mass of each will be represented by the letter m. To increase the speed of their spin, the skater slowly pulls their limbs close to their body. If inertia decreases due to the movement of mass toward the axis of spin, angular velocity must increase for angular momentum to be conserved. Test this yourself the next time you are in an office chair. Hold your arms out and have someone spin you, then pull them in and you will see the increase in speed. Remember, according to hydroplate theory, before the flood, Earth's diameter was slightly larger than today, and its core was not liquid. You probably notice after reading the flood account that months are tracked in exactly 30-day increments. This is common among ancient cultures. In fact, most held to a 30-day month and a 12-month 360-day year. It is curious why they all chose the number 360 if a year has always been 365 1/4 days. However, if as the Genesis flood shows, all these cultures were descended from Noah and his sons, then it makes sense why they would all think a year was 360 days. That is what Noah and his family knew a year to be before the flood. However, the many changes that occurred since the flood have increased the Earth's spin rate. If a day was only 21 minutes longer, a year would match the ancient 360-day calendars. Because observation did not match what was assumed to be a year's time, we see that many cultures had a keen interest in tracking a year by tracking the stars. It must have been very puzzling why a year's length changed. This may be confusing, so I find this simplification helps. Instead of 360 versus 365 days a year, let's just say a year pre-flood was only 4 days long. Because the mass shifted to Earth's center, the angular momentum increased and caused the rate of spin to increase, just like our figure skater example. Note that the velocity of Earth's orbit around the Sun did not change, only Earth's rate of rotation about its own spin axis. In our example, let's assume that post-flood, the rate of spin increased from 4 days to 6 days per year. As Earth's core temperature increased from shifting of materials, the mantle materials with the lowest melting point melted first. As these low melt materials became liquid, crystals of materials with higher melting points became suspended in the melt, but not for long. Gravitational settling began immediately. Dense crystals whose mass was mostly iron and nickel gravitationally settled toward Earth's center. These began forming Earth's solid core. Many of the iron crystals were magnetite. As the magnetite fell through the liquid core to Earth's center, these magnetic crystals were free to align with Earth's magnetic field. This is why Earth's magnetic field is now so strong, and also why seismic waves pass through the core faster when traveling along Earth's magnetic poles than they do when passing in a perpendicular direction. Because the settling magnetic crystals were free to align and tended to align in the same direction, the inner core grew to become a giant magnetic iron-nickel crystal. Unmelted material in the magma, which was less dense than the magma, floated away from Earth's center and rose up until it contacted the bottom of the remaining solid mantle. This slurry mixture of magma-filled sediments became the ultra-low velocity D double prime zone at the base of the mantle, where seismic waves cannot travel quickly through the matrix of both solids and liquid. Because most magma produced was well below the crossover depth, it was compressed to 50% of its original volume. Because of this, Earth's radius has been reduced since the flood. Today, the Earth's average radius is 180 miles less than it was before the flood. The mantle and crust were forced to compress, causing further buckling at the surface, forming additional mountains as Earth's volume decreased like the wrinkled skin of a drying apple. Now that all this has been explained step by step, and by now you've heard and seen much of the explanation and the main points of the hydroplate theory, we can now look at an animation which shows almost everything happening in time. Again, Earth's gravity is the primary driver. This short animation begins as the plates have first split. The sides are eroded away by the fountains. Some critics claim the hydroplates could not have slid because they would have run into each other. Here you can see the erosion of the plates left plenty of room for the initial movement because the perimeters were eroded by several hundred miles on both sides of the crack. Next, the floor of the mantle buckled up, forming the mid-oceanic ridge, beginning in the Atlantic. This lifted the African and American plates as the Atlantic seafloor rose up. Material sheared deep in the earth as the Atlantic floor rose. Near the core, even microscopic movements caused surfaces to melt. The deeper this occurred, the more and more adjacent material also sheared and melted. By the time this reached the Western Pacific, the region of shear and subsidence spanned a wide area, and the entire Pacific plate collapsed and subsided with the fractured mantle as it shifted toward the rising Atlantic floor. This continued and intensified as melted materials in Earth's core contracted, slipped, and melted in a runaway process. Of course, contraction of the core caused contraction of the mantle as well, so while the Atlantic floor was pushing up on the Eurasian, African, and American plates, the mantle was contracting and falling away on the opposite edge of the plate. The plates easily slid down and away from the rising ridge on the remaining lubricating water. The rapid movement soon ceased as plates ran out of water and ground into the dry rock of the mantle, crushed and buckled up, forming compressed mountain chains, while melting much of the rock between the sliding surfaces. Now we can see a second reason the plates could more freely drift. Most of the Pacific plate was pulled down out of the way. The collapsed plate had so many fractures that magma rising from the heavily faulted mantle below spilled out on top of and covered it. So the Pacific plate was pulled down and buried in basaltic magma at the same time. Some 40,000 seamounts formed in the western Pacific above the many fractures. Heat from this magma warmed the oceans for centuries, providing the necessary conditions, along with high continents that had yet to sink into the mantle, to actually start and maintain Earth's only actual ice age. Once these required conditions ebbed, the ice age also ceased. As the core melted and contracted, Earth's volume was reduced by about 180 miles radially. Unmelted sediments in the core settled gravitationally as well, which formed the iron-nickel solid inner core, and the slushy ultra-low velocity D double prime layer at the mantle's base. Let's replay once more to view all at once. Let's now review the main events in the Genesis record in light of the topics we've covered in the hydroplate theory. The flood begins on the 17th of the second month of Noah's 600th year, with the catastrophic rupture of Earth's granitic shell. Deep interconnected chambers of water burst out as great fountains from the deep. Heavy rain falls from the fountains for 40 straight days, then suddenly stops even though the waters continue rising. In the early stages after the rupture, some regions of Earth are buried in supercold hail and muck, trapping, freezing, and preserving mammoths and many other plants and animals. At the same time, Earth's hydroplates are fluttering from the powerful horizontal flow of the ocean of escaping water below. The resulting pressure waves in the granite's quartz produces huge voltages which arc within, producing focused nuclear fusion and fission events, which birth Earth's heavy radioactive elements. The chaotic environment filled with many high-speed subatomic particles bombard the new, fragile heavy nuclei, greatly accelerating their decay rates. The heat generated greatly accelerates the flow of the escaping fountains. Some materials swept up in the violent hypersonic flow of the pulsing fountains are accelerated to such high speeds that they escape Earth's gravitation. An ocean of water, rocks, minerals, gases, dust, and organic remnants are blasted from Earth into the solar system, eventually becoming what are now observed as comets, asteroids, meteoroids, and trans-Neptunian objects. Floodwaters continue to rise even though the rains have stopped, as subterranean waters continue to escape from below. Plants and animals are buried in the muddy waters and eroded sediments. Repeated liquefaction of sediments produces stratified layers in which buried animals and plants are sorted into a sequence that some today mistakenly claim was produced by millions of years of evolution. After about 150 days, the hydroplate's perimeters have been eroded hundreds of miles and have thinned, forming continental shelves and slopes. The mantle floor can no longer support the imbalance from the missing material and bulges up, producing the mid-oceanic ridge. Rapid continental drift begins as plates slide away from the rising mantle floor. Soon the plates crash into the mantle floor as they run out of the lubricating water below. The compression event crushed and thickened the hydroplates and formed mountain chains. As that land thickened and rose, the floodwaters drained into very deep ocean basins. Much of the world's buried plant life is compressed and heated, forming many coal and oil deposits. The big roll of Earth's surface begins. After 150 days, the arc comes to rest on a newly formed mountain rising out of the waters. Meanwhile, the rising Atlantic seafloor causes shearing far below, and Earth's core begins melting and contracting as it extrudes toward the rising Atlantic. The Pacific hydroplate on the opposite side of Earth is pulled deep down under miles of rising magma, which is expanding up from the crossover density boundary. The Pacific seafloor is then covered in volcanic seamounts. A great wind is observed as the atmosphere adjusts to the subsiding Pacific plate and ocean trenches are produced by the deformations. For centuries afterward, heat from the rising magma warms the oceans, greatly increasing evaporation rates. That, in combination with the newly formed continents yet to fully sink into the mantle, cause Earth's first and only ice age. 74 days after landing on Mount Ararat, surrounding mountains finally become visible. Noah begins sending birds out in regular 7-day intervals, observing their behavior. After 314 days since the flood, land is fully visible. Noah uncovers the ark. Apparently conditions are still too unstable to exit. Finally, 57 days later, after 371 days since the rupture, the land is dry and stable enough for all to exit the ark. Unbeknownst to Noah's family, the melting inner Earth is gradually increasing Earth's spin rate. The 360-day calendar they've used to chronologically track these events will soon be obsolete and confuse many generations of their offspring. As the newly formed mountains slowly settle into the mantle, frictional heating melts rock, generating magma. The magma is then injected under the adjacent crust, causing the weakest portions of the crust to fracture and rise to become plateaus. As the thickened continents sink into the mantle, the initially deep ocean floors rise to today's level in compensation for the downward flow of mass. Of course, sea levels rose with the ocean floors, and the continents were divided by water in the days of Peleg. That concludes this overview presentation of hydroplate theory. Hopefully this has been helpful in bringing visual clarity to some topics which can be rather difficult to conceptualize. I'd like to thank Dr. Brown for reviewing this material and providing many inputs which improved the end product. For more information, details, and reference materials, I highly encourage you to visit the Creation Science webpage listed here.